In this video lecture, we are going to be discussing section 6.4 from your textbook, which deals with homogeneous systems of equations. But before doing that, I just want to make sure that you all understand how to read off the solution from a row-reduced matrix. So let's suppose that we were given the following system. So we have a system of 3 equations in 4 variables x1, x2, x3, and x4. Right, so remember what the procedure is when solving this. You take your system of equations and you rewrite it in augmented matrix form. Once you have it in augmented matrix form, you apply row operations until you obtain a row-reduced matrix. So what I have written below is the row-reduced matrix that you would obtain if you had applied the row operations correctly to the system, right, to the system's augmented matrix. So this would have been the matrix that you would have stopped at, because this is in row-reduced form. So let's double check. Does this satisfy the 3 conditions for a matrix to be in row-reduced form? All of the rows of zeros are indeed at the bottom, so that's been satisfied. The second row operation says that, the second condition for a matrix to be row-reduced says that the first non-zero entry in each row must be 1. Here's the first non-zero entry, it is 1. Here's the first non-zero entry in row 2, and it also is 1. In addition, all entries above and below the non-zero entry must be 0, and that is indeed true. Right, the third condition for a matrix to be in row-reduced form says that the leading entry in each row, so here was a leading entry, here's a leading entry, must be on the right-hand side of the leading entry in the row above it, and that has been satisfied in this matrix. So this is indeed in row-reduced form. Now let's read off the solution. Now, in order to read off the solution, you need to take notice of about what each column in here is actually representing. So when you write down the original augmented matrix, you would have taken down the coefficients of x1 and written that down in column 1, x2 and written that down in column 2, the coefficients of x3 for column 3, and the coefficients of x4 for column 4. So that is what each of these columns are now representing. So now let's interpret what this matrix tells us. So the first row in this matrix tells us that 1 times x1 plus 0 times x2 plus 1 times x3 plus 3 times x4 equals to 1. The vertical line represents equality, and I've just written down the constant. Let's now interpret what row 2 is telling us. Row 2 tells me that 0 times x1 plus 1 times x2 plus 2 times x3 plus 1 times x4 equals -2. And row 3 tells us that 0 equals 0, so there's no need to write that down. So looking at these 2 lines that I've written down, let's now simplify what we have here. So we now have that x1 plus x3 plus 3x4 equals 1, and we have that x2 plus 2x3 plus x4 equals -2. Right, so let's rewrite this system in terms of, so we'll write down x1 in terms of x3 and x4, and we'll write down x2 in terms of x3 and x4. So we obtain x1 equals to 1 minus x3 minus 3x4, and that x2 equals to -2 minus 2x3 minus x4. So this is the solution for x1 and x2, and observe something about this. Both x1 and x2 depend on what you plug in for x3 and x4. So x1 and x2 depend on the variables x3 and x4. So that means for every value of x3 that you put in, and for every value of x4 that you put in, you will obtain a new solution for both x1 and x2. There are infinitely many choices for x3 and x4, which means we are going to have infinitely many solutions for x1 and x2. So we place no restriction on what you can plug in for x3 or what you can plug in for x4. Right? So in order to write out the solution, right, so the solution will be written down in parametric form because we know we have infinitely many solutions. Right, so the solution is as follows. We shall let x3 equal to, let's say, t, where t is any real number. We will let x4 equal to s, where s is also any real number. And based on what we have done now, we then see that the answer for x1 is 1 minus t minus 3 times s, and x2 then becomes minus 2 times t minus s. And then of course you could summarize your solution once again. So we have that x1 equals to 1 minus t minus 3s, x2 equals to minus 2t minus s, x3 equals to t, where of course we have t is an element of a real number, so that must be known, and x4 equals to s, where s is an element of a real number. So this is your final solution. Right, that which I've written in the boxed area at the bottom. So ensure that when you have a problem of this nature that you are able to interpret accordingly, and when you have that one variable is dependent on the other, then simply let that independent variable equal to a real number. So write it down in parametric form and then obtain the rest of the solution. Right, so now we're going on to section 6.5. So far what we have done is, given a system of equations, you were required to solve it using the method of reduction. Now it turns out that any system of equations, of linear equations, because that is what we are working with. Right, so any system of linear equations will either be homogeneous or non-homogeneous. Right, so I'm using a term that I have not yet explained to you. Right, so let's define what homogeneous means. Right, so let's suppose that we have a system of equations. So I've written down the first equation in this system. The first equation says that we have coefficient a subscript 1 times the variable x1 being added to a12 multiplied to the variable x2, and of course we are summing in the same sequence, in this pattern, up until we have a1n being multiplied to variable xn. So we observe that there are n variables in this first equation and it's being equal to some constant labeled b1. So you now may ask, why do we have the coefficients being labeled with such a subscript? So if you look carefully at the subscript, the first value in it, so the first one, is now representing the fact that we are in equation 1, and the second one represents the fact that we are multiplying this to the variable x1. So this tells me that this is the coefficient of variable x1. So similarly here, the first one tells you you are in equation 1, and the 2 tells you that you are the coefficient of variable x2. So if we had to write down the second equation in the same fashion and pattern, we would then have that the coefficient will be labeled a21, 2 representing the fact that we are in equation 2, 1 representing the fact that this is the coefficient of variable x1. So plus a22 times variable x2, summing all the way up to variable xn. So the coefficient of xn will be a2n times xn, equal to some constant b2. So right now I've written down 2 equations. So let's say we had m equations. So that means that we're going to have a coefficient am1 being multiplied to x1 plus am2 being multiplied to x2 all the way up to variable xn, so it's amn being multiplied to xn, and this is equal to the constant b subscript m. Right, so we have a system of m equations. Right, so this is a system of m equations in n variables, as you can see. And if I had asked you to write this down in augmented matrix form, or to simply give me the coefficient matrix of this system, you will then observe that the labeling of the coefficients actually makes sense to you, because this labeling system now tells you exactly what entry each coefficient is in the matrix. What will the size of the coefficient matrix be? So let's make a note of that. We note that the coefficient matrix we'll call that A, will have size m by n, because we have m equations and n variables. So we will therefore have m rows and n columns. Right, so that's just something else to take note of. So far I've given you a system, and now we need to define what homogeneous means. So the system given below is called homogeneous if each of the constants, meaning the b1, b2 all the way up to bm, right, because there are m equations in here, right, so each of b1, b2 all the way up to bm are equal to 0. Right, so just to write that down properly, we're saying that b1 equals b2 equals all the way up to bm, and they all equal 0. And based on this definition, we say that the system is non-homogeneous. If at least one of the BMs, right, so I'll just call it BI, one of the BIs is not 0. So for example, if B2 was a number that was not equal to 0, then it will make this system non-homogeneous. So keep that in mind. So let's look at an example. Right, so here I've written down two systems of equations. So here is 1 and here is 2. Right, let's look at the system of linear equations in example 1. Right, so this is a system of two equations in two variables. Right, and remember, what determines whether a system is homogeneous or inhomogeneous? It is the constants on the right hand side. So that is what we have to look at right now. So look at the constants on the right hand side. Is any of them non-zero? And you observe that yes, indeed, there is a non-zero entry in here, and that 10 is non-zero. So because we have a 10 written on the right hand side, this system is non-homogeneous. Right, and what made it non-homogeneous? We'll make a note. It was that, because this is not 0. Right, let's look at the next example. You would observe that everything on the left-hand side of the equality is exactly the same as above. But what's different? We now have that the right-hand side has 0 entries. So this system is homogeneous. Right, so the constants on the right-hand side are 0. We'll use shorthand right-hand side. 0. So that was pretty easy to follow. Right, so now it turns out that when we are working with homogeneous systems of equations, meaning equations where the right-hand side constants are all 0, that we actually have some nice results which will tell you more about the type of solution that you will obtain. Right, so here's a theorem that we're now going to discuss. It says that suppose we have an homogeneous system, right? So we're working with the right-hand side constant zeros of m linear equations and n variables. So that is exactly what I had set up for you before. Right, so now let A be the row-reduced matrix. Right, so it's the row-reduced matrix of, so maybe let's just say the row-reduced coefficient matrix. Right, so what do we mean when we say that A is the row-reduced coefficient matrix? So remember, if you have a system of m equations and n variables, then you can write down its coefficient matrix, right? And thereafter we apply row operations to it until we obtain something in row-reduced form. And that is the procedure that you use when you are solving a system in any case. You write it down in augmented form, but remember that the coefficient matrix is always written on the left of the straight vertical line, which represents equality. So you are in fact row reducing the coefficient matrix. So if we let A be the row reduced coefficient matrix, then we can now state the following. Right, so if A has exactly k non-zero rows, then that k, which represents the number of non-zero rows, must be less than equal to n. And what is n? N is the number of variables in your homogeneous system of equations. So just to be clear about what non-zero means, so it's exactly what you would expect it to be. So a non-zero row, this is a row where all entries are not entirely zero. So at least one entry in the row is not going to be 0. Maybe there was an entry of 6. Right, so that's clearly not 0. Right, so if you count the number of non-zero rows in the row-reduced matrix A, you'll get some number, and we've called that number k. And it turns out that whenever you count those number of rows, that number you obtain k is always less than or equal to the number of variables in the system. But moreover, or in particular, we have the following. We have that if k is strictly less than n, so not just less than equal to, so we're now considering what's happening in there, we are unpacking, then the system has infinitely many solutions. And if k equals n, then the system has a unique solution. And it turns out that the unique solution that you would obtain from a homogeneous system is a trivial solution. What do I mean by trivial? Trivial means that the solution to all of the variables is 0. So regardless of the number of variables that you have, all of them will be equal to 0. And whenever we have a solution of 0 or zeros, we call that a trivial solution. So now why do I expect that the solution will always be 0 whenever the number of non-zero rows equals to the number of variables? Well, remember, a homogeneous system means that the right-hand side constants are 0. So when you're writing down your augmented matrix for an homogeneous system, you are putting down zeros on the right hand side of the vertical line. Then when you are row reducing your matrix, you are applying row operations to the zeros on the right hand side, and any row operation applied to 0 will give you back zeros. So therefore, when the system is in row reduced form, the variables will equal to zeros. So I'll just make a note. Variables equal 0. Okay. Alright, so that is what this theorem tells you. And following from this theorem, we now have a corollary. So the corollary tells you the following. Now firstly, before I state or tell you what the corollary says, keep in mind what k and n represents. K is a number that is giving you information about the number of rows in matrix A, right? Because k represents the number of non-zero rows. So this is telling you something about the rows. And n is a number that is giving you information about the number of columns, because it represents the number of variables in your system. So this represents rows and this represents columns. So it's good to keep that in mind. Now, the corollary tells us that a homogeneous system of linear equations which has fewer equations than variables. Remember, the number of equations is the rows and the number of variables is the columns. So the number of equations is like your k and the number of variables is like n, as I was discussing. Right? So if you have fewer equations than variables, then this homogeneous system has infinitely many solutions. So a homogeneous system which has fewer equations than variables has infinitely many solutions. And these results will come in handy when you're working with a system that is homogeneous and you are predicting what type of solution you are going to obtain. Right, so let's look at an example. Right, so determine whether the following system has a unique solution or infinitely many solutions. Right, so let's look at this system. Firstly, is this system homogeneous or not? Because if it's not homogeneous, then we cannot apply these results, because these results speak to us specifically about homogeneous systems. Right, so we notice that this system is definitely homogeneous because both the constants on the right hand side are definitely 0. Right, so the above system is homogeneous. Right, so we can apply those results. Now let's take a look at the size of the system. So how many equations and how many variables? We have 2 equations and 3 variables. Right, so the variables are x, y, and z. Right, and what does our previous results tell us? So our corollary says that when you have an homogeneous system and you have fewer equations than variables, meaning there's more variables than equations, then the solution is infinitely many solutions. Right? So in here, the number of equations is definitely less than the number of variables. 2 is less than 3. Right, so therefore, by our corollary, we can conclude that the above system has infinitely many solutions. Alright, and this is where I will be stopping. I will be posting a tutorial on Blackboard, so please ensure that you download it and practice with those questions.